The CCNY Robotics Lab is developing the City Flyer for research on 3D mapping for micro-UAVs at the Grove School of Engineering. The City Flyer is a quadrotor research platform based on the Ascending Technologies Pelican micro-UAV airframe. Additional sensors have been added to support our 3D mapping research. A Swiss Ranger 4000 and a Logitech C600 webcam are combined to create an RGB depth camera. The weight of the Swiss Ranger makes this sensor configuration incapable of flight using the current airframe. However, we anticipate that advances in small-scale RGB depth cameras will solve this problem. The aim of this paper is to build three-dimensional maps of indoor environments. In order to build accurate 3D maps, we need to estimate the full 6 degree of freedom pose of the vehicle. The altitude is obtained directly by an altimeter. The IMU provides the roll and pitch information. Through a series of steps, the IMU and Hokkyo laser are used to produce the X, Y, and horizontal heading components of the 3D pose. After obtaining the full pose estimate, we incrementally build a 3D map using a filtered point cloud data provided by an RGB depth imager. We store the map data in a novel structure called a multi-volume occupancy grid, or MVOG.
We begin by using the roll and pitch estimation from the IMU sensor to project our laser scan onto the XY plane. We assume a rectilinear indoor environment where the scans do not change at different heights. This allows us to perform accurate scan matching in 2D regardless of the 3D pose of the vehicle. Scan matching is a critical step in our algorithm. While UAVs can estimate their height and angles of orientation through an altimeter and IMU, the displacements in the horizontal plane cannot be determined directly. By applying a 2D scan matching between readings, we can accurately calculate these missing components in the full robot pose. We demonstrate that this odometry-free and GPS-denied approach successfully achieves loop closure by using a particle filter-based SLAM technique.
The combination of the Swiss Ranger and color camera allow the spatial and color information to be fused. This will improve segmentation of the data, which may be useful for future research. The point cloud returned by the Swiss Ranger is filtered by applying a threshold filter on the confidence information returned by the sensor. The point cloud shown in blue represents the raw data returned by the sensor, while the orange point cloud shows the data after applying the filter.
We fuse together the point cloud data of the Swiss Ranger camera into a multi-volume occupancy grid. Readings are grouped together into continuous vertical volumes placed on a horizontal grid. Obstacle readings create positive volumes displayed in red. Similarly, free space readings are grouped in negative volumes, displayed in blue. Additional sensory data increases the occupancy value of the corresponding positive or negative volume. By taking the ratio between the positive and negative values, we can create occupancy grids for any arbitrary altitude. This novel map structure is robust to noisy sensor readings and allows us to store our data in a very space-efficient manner. The entire pose estimation and mapping process results in a 3D map that can be used for the purposes of obstacle avoidance and path planning. The algorithm ran in real time on a desktop computer. The most computationally intensive step is the scan matching between poses. The speed of the helicopter needs to be sufficiently low in order for the scan matching to converge and produce an accurate motion estimation.
We would like to thank our sponsors for funding and to thank you for watching.